Yeah, I think it will.
Okay. Okie dokie. So let me just add a page. All right, you guys, does anyone, first of all, have any questions about the differentiating with respect to T? Or was that pretty straightforward? Okay. So then if we're okay with it, I'm going to kind of jump into related rates. So I think I put a couple just so that I didn't blank out for introducing what related rates problems are. But let's think about the situation. Let's say you have your water bottle, okay? And you're filling your water bottle at the water station at school. And let's say that you started a stopwatch, okay? To time as you're filling your water bottle. And your water bottle started as empty, okay? So you start your stopwatch, although that's not really necessary. And the water fills and you stop once it's full. What are some quantities that would be changing as you're filling the water bottle? Like as time is passing, what are some different characteristics or quantities that would be changing?
Volume.
The volume of the water in the bottle. Does everyone agree with that? Anything else? So when you first start filling it, the water level is really low, right? And then as time is passing, your bottle is going to get fuller and fuller, like the volume is going to be increasing. But how about the height of the water in the bottle? That would also be increasing as your volume is increasing, right? And then if we think, okay, well, what other quantities could we think of in terms of a water bottle? Like I'm thinking of like a cylinder water bottle. Well, if it's a circular water bottle, you could measure what the diameter of the water bottle is or what the radius of the water bottle is, right? The radius would be half of the diameter. As time is passing and you're filling the water bottle, would that quantity be changing? No. So the diameter of the water bottle or of the water that's in the water bottle would stay the same. However, the volume and the height of the water or the water level would be changing. Both of those values would be increasing. So there's a relationship between the volume, or you could come up with a relationship, like an equation that would represent the volume of the water that's in the water bottle, right? And there's also a relationship between the rate at which the volume is increasing and the rate at which the height is increasing with respect to time. And when I say with respect to time, I think back to when I was saying with respect to before. I would say, okay, we're going to find the derivative of y with respect to x. Well, now when I'm talking about the rate at which the volume of the water bottle is increasing, that's the rate at which the volume is increasing with respect to time. So how the volume is changing as time is changing, right? The derivative of y with respect to x was how is y changing as x is changing with respect to how x is changing. So we always said derivative of y with respect to x could be written as a dy over dx, right? Derivative of y with respect to x. That's a formula that tells you how y is changing with respect to how x is changing. Well, if we want to know something like how the volume is changing with respect to time, the way that we could represent that would be dV over dt. If volume was represented by V and time is represented by T, then the formula that you would be looking for would be dV over dt, what that's equal to. And that would tell you how volume is changing with respect to how time is changing or how time is passing. The one other example that I put on there, and usually if we're in person, I get balloons for this day of class and we all blow up balloons and talk about like what's changing, but obviously we can't do that. So let's say that imagine a balloon being filled up on like a tank with a tank of helium. Okay, so air or helium is being blown into the balloon and the balloon is blowing up. What are some quantities that would be changing as you're imagining the balloon being blown up?
Diameter?
Yeah, the diameter of the balloon would be increasing, right? Anything else?
Surface area?
Ooh, that's a good one. The surface area of the balloon would be increasing, right? As the balloon is stretching and filling. What's it filling with?
Air.
Right. So as it's filling with air, we could say that the volume of the balloon is also changing, or more specifically, it's increasing. Okay. And those quantities are all related. And so we can also think about the rates at which they are changing, the rates at which those quantities are changing with respect to time are also related. So this is just section 3.3 part 2. We're going to be in section 3.3 part 2 until break. So until the end of next week. Okay. So we're going to be solving related rates problems. And those are problems that involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known. That might sound confusing. But basically, these problems, you're given a situation where you're also given a rate at which a quantity that's related to the situation is changing. So you have to know at least one rate usually. And then you're going to need to solve for a rate that is unknown and is related to the given rate. Were we able to follow that okay, or should I try saying that again? So you're given a rate and you're trying to find an unknown rate based off that given information. And that rate that you're solving for is related to the given rate. Okay, so we're going to be using implicit differentiation to determine the rates of change, often with respect to time. So that's why I had you guys do the assignment where you were differentiating with respect to t, because that's what we're going to be doing going forward. And when we differentiate with respect to an independent variable, which is usually time, actually all of these examples, all the problems you're going to be working with are differentiating with respect to time. We're deriving the relationship between the rates of change. So if you are either given the relationship between the quantities that are changing, so like if you're given the formula for volume of a cylinder, okay, that tells you, that equation describes the relationship between the volume and the volume of the cylinder and, or whatever's in the cylinder and its diameter. Or you might be given some extra information that then relates like the height of the cylinder and its radius. But then when you take the derivative with respect to time of that relationship, you're coming up with an equation that describes the relationship between the rates of change. So like the rate at which volume is changing and the rate at which the diameter is changing, or something like that. And you guys just stop me if you have any questions. So we're going to start with this very simple example. It's the moving particle example, okay? So I want you to try and visualize a particle moving along a graph. The equation that I give you actually represents a hyperbola. And if you guys remember, hyperbolas are the ones that can either, they're conic sections, and they're the ones that can either open both out or up and down. This one in particular opens out. So if you can imagine a particle moving along the graph, and again, you're thinking about having this extra component of time. So as time is passing, the particle is moving around the graph. So when the particle is at the point 5, -2, its x coordinate is increasing at a rate of 3 units per second. How fast is the y coordinate changing at that moment? So in this example, we're given the rate at which the x value is changing at that moment in time. And the moment in time is described by the position of the particle in the graph. So we're given the rate at which the x coordinate is changing. It's actually increasing at a rate of 3 units per second. And we are going to solve for how fast the y coordinate is either increasing or decreasing with respect to time at that particular moment. So you'll see, I go through the same set of steps for all of these problems. And I have it laid out or numbered, the steps, on the next slide, and we'll go through those in a minute. But we are given, I always like to state what we are given. We're given the rate at which x is increasing. So the rate of change of x with respect to time can be represented as dx over dt. And that rate is that the x coordinate is increasing at a rate of 3 units per second. Since x is increasing, that rate is going to be equal to +3 units per second. And if it were decreasing, we would say it's equal to -3 units per second. And then I like to state the rate that we're trying to solve for, because remember I said for these related rates problems, you're given one rate, or at least one rate, and you're being asked to solve for another rate. So we're given the rate at which x is changing, and we want to find the rate at which the y coordinate is changing. So that means we're trying to find what?
dy over dx.
Not dy over dx. Close though. So remember, say that one more time.
dy over dt.
dy over dt. We want to know how y is changing with respect to time. So the units on dy over dt will be units per second, just like they were for dx over dt. And we're trying to find dy over dt when the particle is at the point 5, -2. That describes the when. So we've stated the given, we've stated what we're trying to solve for, And then now we're going to actually take this equation, oops, and we're going to differentiate with respect to t so that we can derive that relationship between the rates of change. So first step, I'm stating that I am differentiating each term with respect to t. Remember, for your test and what we were doing before, I had you guys do this as your first step because it wasn't always going to be us differentiating with respect to x. Okay. So now thinking chain rule, we're going to differentiate. So for this first term, I'm thinking of the square as being the outside function and the x as being the inside function. So I bring the 2 down, I subtract 1 from the exponent, I leave the inside alone, and then I multiply by the derivative of the inside with respect to t. The derivative of x with respect to t, I write as dx over dt. And then moving on. So when I multiply, I'm going to multiply the -4 by 2. So that I'll have -8. I subtract 1 from the exponent. I leave the inside alone. And then I multiply by the derivative of the inside with respect to t, which would be dy over dt. And the derivative of the constant 9 with respect to t will just be 0, just like before. So just cleaning that up a little bit, that's 2x times dx over dt minus 8y times dy over dt equals 0. And then we're trying to find dy over dt. So let's go ahead and solve or get dy, ooh, it's not very easily seen. Let's get dy over dt by itself using algebra. So I'm going to subtract 2x times dx over dt from both sides. And then you can either think about dividing by -8y on both sides or multiplying by its reciprocal, -1 over 8y. But you end up with dy over dt is equal to positive x over 4y times dx over dt. Does anyone have any questions about how I got here? Okay, so at this point, we have the formula for the derivative of y with respect to time. And we can just plug values in. So I'm going to use the highlighter to show what I'm plugging in. So I'm going to plug 5 in for x and -2. Oh, I keep using the pink and I shouldn't use the pink. No, I already used green. -2 in for y. And then we're given dx over dt. So we can plug in 3 for dx over dt. And when we simplify that, we get negative 15/8. And that's the rate at which y is changing with respect to time in seconds. So the units will be units per second. And then this is a word problem, so we do want to summarize with a sentence. Just trying to shrink this down a little bit. And I think that summarizing with this sentence also helps us understand like what these numbers mean, what this number means. So we can say that the y coordinate is decreasing because we got a negative rate. So it is decreasing at a rate of 15/8. I don't need to put negative 15/8 because I've described the negative by saying the rate is decreasing. So 15/8 units per second. When the particle is at the 0.5 comma -2. That describes the moment in time. Because remember, derivatives give us instantaneous rate of change. So change at a particular moment in time. Does anyone have any questions? All right, you guys, then we're gonna keep going. So this is the general method that we're going to use for solving related rates problems. So if I haven't provided you with a picture, you want to try and draw a picture if possible, and then label with the different variables that you want to use or any of the given quantities that you know. And oftentimes I will give you guys a picture, but you might need to label it. So then you want to think, which rate do we want and which rate do we know? So kind of like in this example up here where I stated what rate I was given, and then I stated the rate that we were trying to find. And then we want to find the relationships between the quantities that are true for all times in this problem. So basically come up with the equation that gives the relationship between the quantities that you care about. And the goal is to have a complete chain between the quantity whose rate we know and the quantity whose rate we want. So what I mean by number 3 is we want to come up with an equation that has the variables of the quantities that we care about. So it has the variable, like if you're given the rate at which volume is increasing or decreasing, you want to have volume in the original equation, because you're going to need to take the derivative with respect to time and be able to plug in dv over dt. If you're trying to solve for the rate at which the radius is changing, then you want to have r representing radius in that equation so that then when you take the derivative, you'll have a dr over dt that you can solve for. So step 4, we're taking the derivative with respect to time. Step 5, you're plugging in values for the moment in time that we care about. So up here, notice I didn't plug in the 5 and the -2, well, we couldn't plug in the 3 until we differentiated. But I didn't plug in any values until the end. The only time you can plug in a value before you differentiate is if that quantity is not changing as time is passing. So like if we think back to the water bottle scenario of like you're filling your water bottle, your cylindrical water bottle. Remember we said the volume was changing, the height or the water level was changing, but the diameter was not changing, or the radius of the water that's in the bottle was not changing. So that's something you could plug in the value of the radius if you wanted to, because that quantity would not be changing as time is passing. That's the only time you can plug in a value before you differentiate. And then you want to solve for the rate that you are looking for. So we're going to do 2 more examples together. And I apologize if I'm going too slow. Just get my notes caught up. Okay, so we're looking at the melting snowball example. Switch colors, blue. So a spherical snowball, so this is one of those things we're simplifying. We're assuming the snowball is a perfect sphere. So a spherical snowball with an outer layer of ice melts so that the volume of the snowball decreases at a rate of 2 cubic centimeters per minute. How fast is the radius changing when the diameter of the snowball is 10 centimeters? And we're given the formula for volume of a sphere is V equals to 4/3 pi times r cubed. So the first thing that I'm going to do is I'm going to state the rate that I'm given. So I'm given that the volume of the snowball decreases at a rate of 2 cubic centimeters per minute. So volume, rate at which volume is changing, is going to be represented as dV over dt. And since the volume is decreasing, I know that that rate is going to be negative 2 cubic centimeters per minute. We want to find or solve for how fast the radius is changing. So we want to find dr over dt when the diameter is equal to 10 centimeters, which if the diameter of the snowball is equal to 10 centimeters, so that's describing the moment in time. So at the moment that the diameter of the snowball is 10 centimeters, we want to know how fast or like how the radius is changing with respect to time. And we know that if the diameter is 10 centimeters, that means that the radius would be 5 centimeters at that moment in time. And notice that the equation for volume of a sphere has V and has R in it, which is great. We're set up to where when we take the derivative, it'll have a dV over dt and a dr over dt in it. Does anyone have any questions about how I stated the given rate and the rate that we're trying to solve for? Okay, so let's differentiate with respect to t. I'm going to pull the 4/3 pi out front since that's a constant. Okay, well, the left-hand side is just going to be dV over dt. And then if we think chain rule for differentiating the right side, that will be 4 pi, right? Because we multiplied the 4/3 by 3. We leave the the inside alone. Oh, sorry, we've subtracted 1 from the exponent. And then we multiply by the derivative of the inside, which would be dr over dt. The V doesn't look like a V. I'm going to fix it. So we are trying to solve for dr over dt. So it's up to you at this point. If you want to plug in, after you've differentiated, you can plug in values. Or if you want to get dr over dt by itself first, you can. I think it's a little bit easier to deal with the numbers. So I'm going to actually, since I've differentiated, I'm going to plug in values now. So I'm going to be plugging in the -2 for dV over dt. And I'm plugging in 5 for R. So that ends up being -2 equals to 100 pi, because it's 25 times 4. And now I can see, okay, if I divide by 100 pi on each side, I'm going to flip this around. I'll get that dr over dt is equal to -1/50 pi. And to determine what the units are, you can think, okay, well, what units is R being measured in? Centimeters. And then what unit is time being measured in? So, and that is minutes. So centimeters per minute would be the units. So to summarize, we could say the radius, oops. No, we could do that. So we could say the radius is decreasing since we get a negative rate. At a rate of 1/50 pi centimeters per minute when the diameter of the snowball is 10 centimeters. Or you could say when the radius of the snowball is 5 centimeters. You should describe what the moment in time is. Any questions? So my plan is to go through one more with us all together. This one shouldn't take that long. Okay, the sliding ladder, classic related rates problem. Okay, so if you imagine a ladder leaning against a wall, and then if you're standing on the ground and you think about pushing the base of the ladder towards the wall, the top, you can probably imagine the top of the ladder would end up sliding up the wall. Or if you think about pulling the base of the ladder out towards you or away from the wall, then the top of the ladder would end up sliding down the wall. Okay, so we have a ladder that is 20 feet long leaning against a building. I'm going to draw a picture of this. Okay, so that's the ground, the wall, draw a red ladder. So here's my oops. Keeps just trying to like blend with the other line. Okay, so that's a 20-foot long ladder. If the bottom of the ladder slides away from the building horizontally at a rate of 4 feet per second, how fast is the ladder sliding down the house when the top of the ladder is 8 feet from the ground? Okay, so this is pulling the bottom of the ladder out at a rate of 4 feet per second, and we're solving for how fast the ladder is sliding down the house or the building. I don't know why I switched from building to house. So I'm going to label this picture. I'm going to label the distance of the bottom of the ladder to the wall as being X. You can use any variable you want, but I'm going to use X. And I'm going to say that the distance from the top of the ladder to the ground is Y. And as time is passing, those quantities are changing. Now notice what shape is created in our picture.
Triangle.
What type of triangle?
A right triangle.
A right triangle. And we know the relationship between the sides of a triangle is referred to as the Pythagorean theorem. Okay, so we're going to hold that thought for 1 second because we still want to state the rate that we're given and the rate that we're trying to solve for. So we are given that the ladder is sliding away from the building at a rate of 4 feet per second. So that's how X is changing. As time is passing, since the ladder is sliding away from the building, is X getting larger or smaller?
Larger.
It would be getting larger. So that tells us that dx over dt is going to be positive 4 feet per second. If it were being pushed in towards the wall, then X would be decreasing and our rate would be negative 4 feet per second. And we want to find the rate at which the ladder is sliding down the wall of the building or the house. So we want to know how y is changing with respect to time. So dy over dt. When the top, at the moment when the top of the ladder is 8 feet from the ground. So that's when y is equal to 8 feet. Okay, so the relationship between the quantities, I didn't give you a formula or anything here, but like Lizzie said, this is a right triangle. The relationship between the sides, the three sides, can be described with the Pythagorean theorem. So x squared plus y squared, right? The sum of the legs squared is equal to the hypotenuse squared. And we can simplify that. That's x squared plus y squared equals to 400. So we've stated the given rate. We've stated the rate that we're trying to solve for and when. We have our relationship between the quantities that are changing. So now we're ready to differentiate with respect to t. Okay, so that'll be 2x times dx over dt plus 2y times dy over dt equals 0. Okay, so I'm gonna highlight. So I know dx over dt, I can plug 4 in for dx over dt. I know we're finding dy over dt when y is equal to 8. So we'll be able to plug in 8 for y. The thing is, we're missing what x is, like what we could plug in for x. But we can figure out what x would be at the moment that y is equal to 8 feet by using our Pythagorean theorem relationship. So we could plug in, we can solve for what x would be by plugging in 8 in for y. So that would be, I don't have a calculator by me. That would be x squared equals to 336. So x would be equal to the positive square root of 336 feet. I'm just going to leave it like that. And I'm going to plug in the positive square root of 336 in for x. So plugging all those values in, okay. And then just simplifying a little bit, that would be 8 root 336 plus 16 times dy over dt equals 0. So then to finish solving for dy over dt, oh, no, over 2, not 8, over 2. Okay. And if you were to just type that into your calculator, you would get negative 9.165. I'm going to give myself one more piece of paper, one more page. And the units, well, y is being measured in feet and time is being measured in seconds. So feet per second. So to summarize, we could say the top of the ladder is sliding down the building or the house at a rate of, and I said it's sliding down. That describes the negative. So I don't write the negative in my sentence. I put at a rate of 9.165 feet per second. Oh, when the top of the ladder is 8 feet off the ground. So again, I described the negative part of the rate by saying that the ladder is sliding down the wall, down the building. Does anyone have any questions? So I have videos posted for the water tank example. This one's pretty short. It's like a 5-minute video. And then the sand pile, there's 3 different parts. So it's like a 15-minute video. But I'm gonna let you guys go so that you can watch those videos. And then it's just 2 problems from the textbook that I want you to attempt. And my solutions are posted. I will be here until 9:33. If anyone has any issues or wants to talk about any of the examples, but otherwise you are welcome to log off of Zoom.
Thank you.
Thank you.
Thank you.
Thank you.